Okay? And this species here, which is an enol form of the corresponding keto form, you've seen this kind of proton shift called tautomerism in chapter 13 when we talked about enols going to ketones. So this goes to that, and this is the other product. But the point is, this generates a low concentration of Br2. So experimentally, you take, for example, cyclohexene, NBS, you put light on it, or radical initiator and COMTET, you boil it up, out comes allylic halogenation. That's your piece of vocabulary. NBS plus an alkene gives you the allylic halide. High yields, and the side product, the other product, is this stuff which you then recycle. So one can show this in an animated way. So here it is, first the generation of Br2 by the HBr attacking the NBS. So that's your Br2. That's the crucial species that you need as your reagent. In high dilution in the mixture, light in this case splits this. This can be done thermally also. Br dot then attacks your allylic position. That's the weak bond. Pulls off H, makes this dot. That's the allylic radical. Stabilized by resonance. Attacking now Br2, that generates your product, bromocyclohexene. And the Br dot goes back in the propagation cycle to attack another mole of starting material to just repeat the step. So in principle, all you need is one Br atom to actually turn over all of cycloalkene, in this case, to the corresponding bromocycloalkene. Now notice that because the radical that we're generating here is actually a bifanged radical, because it's allylic, such that both termini of the allylic system have dot character connected by resonance forms, right? Reactivity can occur at either carbon. For a symmetrical system, like in the allyl radical itself, or 2-propenyl, the 3-carbon system that we looked at the very beginning, or for cyclohexene, it doesn't matter. Both ends are the same. The system is symmetrical. It doesn't matter which carbon reacts. In fact, they both react 50-50. But if you have an unsymmetrical double bond, the intermediate radical is unsymmetrical, and the two products formed by attacking at either terminus will be different. Do you get mixtures? Yes. So this is a problem in synthetic applications. For example, this terminal 1-octene with NBS and peroxide makes as an intermediate this radical. Resonance stabilized. We have dot at this carbon as well as dot at this carbon. Bromine traps this radical such that it will react both at this carbon as well as this carbon, and the outcome is about, 3-to-1 mixture or 4-to-1 mixture of the two components. Okay. We shall see that one can tinker with this a little bit, control the so-called regioselectivity of the products by converting them further later on. But in the radical halogenation, you will get a mixture. Okay? So this is something to consider if you want to use this reaction in a synthetic scheme. Best would be to have a symmetrical starting material or symmetrical intermediate allylic radical. SN1 reactivity. Indeed, you take this chlorobutene and you dump it into water and wait, and it will spontaneously dissociate, even though it's a primary chloride. And it will do so because the primary carbocation is really a special primary carbocation. It's stabilized by resonance. This is the second resonance form. Okay? So it's an allylic cation. And therefore, again, we have reactivity at this carbon as well as at this carbon. They're both delta plus, if you wish. And so water will trap these two products to make two products, two allylic alcohols. SN2 is also accelerated. Why is that? There are two reasons for this. One is And first of all, let's look at the experimental result. You take the same chlorobutene that we saw earlier that undergoes SN1 reactions in just water. Water is a poor nucleophile, so SN2 is too slow, SN1 wins. If you dump in a good nucleophile, SN2 is faster than the SN1, and you'll get nucleophilic substitution to make this iodide. If you look at the relative rates, compare this with the corresponding saturated system, chlorobutane versus chlorobutene, it's about 100 times faster. Okay? So the double bond gives you a 100-fold kick in the SN2. Why? One reason is, there are two reasons. One reason is that this carbon increases the delta plus character of this carbon, which is the reacting carbon, making I- even more eager to attack that carbon relative to this carbon. Why does it make it more delta plus? Because compared to this carbon, it's sp2 hybridized. This carbon is sp3 hybridized. sp2 versus sp3 means we have more s character. The more s character means the orbitals are held more closely to the nucleus. It means electron withdrawing. This was the reasoning we used at the end of Chemistry 3A, Chapter 13, to explain the acidity of alkynes. That carbon is sp, 50% S character, making terminal alkynes unusually acidic, pKa on the order of 28 or 29, okay, compared to an alkane with pKa of 50. So going from sp3 to sp2 makes this carbon electron withdrawing. That means this carbon is relatively electron poor relative to this one. Iodide attacks it even faster. In addition, the second explanation is a transition state explanation. In the transition state for the SN2, remember, is bimolecular, and it goes with inversion. The carbon that is being attacked, so here's the nucleophile coming in, and here's the chloride leaving in the transition state, is actually sp2 hybridized. You can go back to Chapter 6 and look at that picture, the typical umbrella inversion type motion. So making this sp2 hybridized, of course, means that this p orbital in the transition state will interact with the double bond p orbitals. So the transition state is actually stabilized relative to the system in which this is saturated. There are no p orbitals here. And that also accelerates the SN2 slightly. So there are two reasons for that. And then we have allylic organometallics. That is, we have unusual acidity of the allylic CH bond. If you take this 2-methyl propene and treat it with butyl lithium, when it gets protonated, makes butane. pKa of butane is 50. pKa of this is 40. So this equilibrium constant is 10 to the 10 to the right. Butyl lithium will pull off this proton to make the more stable anion. And that anion is a typical alkylithium reagent, can be used as we've used it in Chapter 8 and subsequently aldehyde additions, for example, to make alcohols and so forth. There is, of course, another way of making allylic anions, namely through allylic metallation, such as in Grignard formation. With magnesium, you just get the normal allylic magnesium reagent. So that's a complementary way of doing it. And we shall see, this is the anion that we get, the allylic anion, stabilized by resonance. We'll see many neutral analogs of allylic anions where we have a double bond with a heteroatom next door that bears an electron pair, such as oxygen, sulfur, and nitrogen, where this electron pair can be donated, just like in the anion, to make a new resonance form. In this case, of course, since you're starting with neutral, it's a resonance form that is dipolar, plus on X, minus on carbon, a minor resonance form, but it explains a lot of the reactivity of allylic systems. So to finish this off, let me show you a handwritten low-tech mechanism of the allylic halogenation. If you wanted to show this in an exam, the bromocyclohexene formation with bromine in low concentration, you would start with the initiation step, which is splitting the Br-Br bond. We use fishhook arrows, remember, for radical reactions. That makes 2 Br dots. So this is step 1, which is the initiation step. The bromine dot is the one that turns things over. So then we attack cyclohexene with Br dot. We make a bond between this dot and one electron derived from this electron pair that makes up the CH bond. That generates HBr, one of the products of the allylic halogenation. And this dot, which is stabilized by resonance. And then that's step 1 of the propagation. Step 2 regenerates Br dot by the allylic radical reacting with bromine. And you split this Br-Br bond to make the bromocyclohexene plus Br dot. And I think that's enough for a